Uh, so this is day 4 class of the computer architecture course. Then actually I recorded the day 3 class, and then I posted the day 3 class on the YouTube. I hope everyone watched the day 3 class, because in the day 3 class, we covered the performance, and then how to measure performance, and then how to compare performance of two different computer systems. Actually, this is very important because, so as I mentioned, the goal of the computer architecture research, it's the main goal. So the main goal of the computer architecture research is to increase the performance of computer systems and reduce the cost. The cost includes the running cost or manufacturing cost. So these are the main goals of engineering research. Okay. Also, please turn on your camera, because and then hopefully, so I will provide the in-person lecture, that means offline lecture, in the next class. So, but I will also provide the online class because as I mentioned in the first class, so maybe the COVID-19 situation is very serious, and then actually the many students, I think many students are tested positive recently. So I will also provide also online classes. Maybe I will. So actually, the next class is the first class of the in-person lecture. So I don't know how smoothly the lecture the lecture will be provided. But okay, so in the next class we will have in-person lectures. Okay. So in the previous class, that means the day 3 class, it's a recorded class. So we learned about the performance of computer systems, and then that means how to measure the performance of a processor or computer systems. So firstly, I mentioned the two different metrics of the performance. The first metric is response time. That means how long it takes to do a task. So it's a response time. That is also called the execution time or latency. Also, another performance metric is throughput. So that means the amount of total work done per unit time. So there are two different metrics. So please remember the definition of response time and throughput of a system. Actually, these two terminologies are frequently used in our real life, actually, in the engineering field. Okay. Also, we learned the definition of performance. So what is the performance? The performance is the inverse of execution time. This is a definition. So please memorize it's just the definition. So please memorize the definition. Okay. I cannot explain about this performance, but so in the real life, we frequently say, oh, my computer system is very fast. That means my computer's performance is very high. Okay. Then how can you compare the performance of two different systems? So we can just compare the execution time. Okay. But the performance is inversely proportional to the execution time. So the performance X over performance Y is equal to execution time of Y over execution time of X, because it's inversely proportional. So you need to remember. Also, we focus on the CPU time. Okay, so I briefly read what we learned in the previous class. Okay, so actually in this course we focus on the CPU time. So what is the CPU time? So computer is composed of CPU and any peripherals such as the memory systems or networks, I/O systems such as mouse and mice and keyboard. Okay, but if we also learned that the computer system is composed of many layers, and then actually the overall performance of this computer system is influenced by different layers. Okay, like operating systems or I/O devices or networks, blah, 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 and so on. So it's very hard because this performance is changed by the different situations or different environments. So in this course, we just focused on the performance of a processor. So what does that mean? Is any different parts, any different peripherals are ignored. So we just focus on the how applications are run, how applications run on the CPU only. Okay, so any other part such as the operating systems are excluded. So any I/O devices or I/O interrupts are also excluded from this performance. Okay. And then what is the CPU time? So the CPU time is also the inverse of the execution time of application that runs on a CPU. And then we also we can consider the two different factors such as the CPU cycles and then CPU cycle time. So that means we meet these two factors like a CPU number of CPU cycles and clock cycle time, that is the clock period time. So we can calculate the CPU time. Then why do we divide the CPU time with some two different parts like number of clock cycles and then clock period? I explained that. So this part, the clock cycle, number of clock cycles is influenced by normally software. Okay. Also, So this, what I said normally. So these CPU clock cycles can be also influenced by hardware or architectures, but I said normally. So usually or normally, CPU clock cycles are influenced by software part. And how about this clock period? Clock period is influenced by hardware part. Okay, that's why we divide this CPU time equation as two factors. Okay, and then, so actually, in the performance part, this equation is the most important equation. So actually, it's very so we can calculate the number of clock cycles as the instruction count multiplied by cycles per instruction. But it's obvious actually. So it's obvious, right? So why do we need to divide these clock cycles as the two parts? So also, if we divide some factors, then we can focus on some specific factors that can influence the performance of computer systems. So we can calculate the clock cycles like instruction count multiplied by cycles per instruction, it's CPI. And then this instruction count is IC. So number of clock cycles is IC multiplied by CPI. Why? Why do we divide? Because instruction count, it's also normally. Instruction count is primarily influenced by software part, and CPI is influenced by architectural part. Okay, so if you check the size of some applications such as Google Chrome, then you can find the size of the binary file of Google Chrome, right? The Chrome web browser. So actually the instruction count is not always proportional, but usually proportional to the size of the binary file. Okay, so that is the software part, not hardware part. It's purely software part. So instruction count is influenced by the kind of software, also some other factors such as the compiler options, and then instructions and architectures, blah, blah, blah. Okay, also algorithm, the algorithm of an application. And how about the CPI? CPI is also influenced by software and architecture. Okay. So we also I also covered the CPI in more detail. How can we calculate the CPI from the some provided information such as this slide. Okay, so I also mentioned that the CPI is influenced by software part because the different software includes the different fractions of instruction classes, right? Like this. So these are the instruction classes like A, B, and C. And then different instruction classes may have different CPI values, like this example, right? And then different applications or different program will have different fractions of also these instruction classes, right? So some applications may have lots of load instructions, like memory transfer instructions, but some applications may have lots of computation instructions, such as arithmetic or logical instructions, right? So, and then different kinds of instructions may have different CPI values. So also the CPI is influenced by software, okay? So just remember the definition of CPI. CPI is just clocks per instructions, okay? That is the averaged value, okay? So in conclusion, so performance summary, we can calculate the CPU time like instruction count multiplied by CPI and multiplied by clock period, so clock cycle time. So we can easily write this equation like execution time equal IC CPI multiplied by T. And then, as you can see, different factors influence these different components that decides the performance of computer systems. Okay, so as you can see, this slide's algorithm, that is the software part, was influences instruction count normally, and then possibly CPI. And how about the programming languages such as C or Python? Instruction count and CPIs can be influenced by programming languages. How about the compiler? Also affects the instruction count and CPI. Architecture affects the influences everything. Okay. So another performance metric is MIPS. That is this slide will be newly covered by this class. So this is the new part of the today's class. Okay, so we can use the another performance metric called MIPS. So MIPS means the millions of instructions per second. So we can easily say, oh, MIPS, the unit of the MIPS is the instruction count divided by time, like second. So because it's a second. So MIPS just mentions the how many instructions are executed during unit time. Okay. Then can we use this MIPS as the some performance metrics, like exact performance metrics? So we can think like this. So this is the computer A, and this is the computer B. And then computer A can execute 100 instructions per second. Okay, 100 million because it's a MIPS. And then computer B can execute 50 million instructions per second. Then which one is the faster? Which one is faster? Okay. Yeah, someone answers A. Is it always true? It is not always true, actually. Why? Let's focus on the, so this is the different computer systems, and then A can execute the 100 million instructions per second. But this is the same application, like app. It's the same application. And then application is written in high-level language. And in order to execute this application, then we need to compile this application. That means the code written in high-level language is translated into the machine code, right? So that means instructions, right? So this same app can be compiled with, so for example, x86 instructions, or the same app can be compiled with ARM compiler. Then how many instructions are generated for these two different cases? We don't know. So usually the x86 is the complex instruction set. So usually, so we expect that if the same application is compiled using x86 compiler, then number of generated instruction can be smaller. But I said usually, not always. Okay. So for example, it's the same app. So the same app is compiled. So for this x86 with this x86 compiler, the size of compiled binary file can include 25 million instructions. And then how about the ARM? Maybe this application include 100 million instructions. And then this code is executed by computer B. And then this code is executed by computer A. Which one is faster? So in this case, so yeah, right. It will take 1 second if the same application is executed by computer A, but it will take only 0.5 second. Okay, do you understand? So do not be confused. So we can use MIPS as performance metrics if ISA is the same and compiler options are the same. Do you understand? So the same application should be compiled. Then this application can be executed by computer processor, and the application instruction count is influenced by compiler and ISA. Okay, so we don't know how many instructions are generated after compilation. Okay, that is the problem. So if ISA is the same and compiler options are the same, then we can use MIPS as the performance metric. Okay, you can simply, oh, MIPS number is very high. If MIPS number is higher, well, then we can say, oh, this computer have higher performance. If instruction set architecture is the same and compiler options are the same. Okay, so do not be confused. So if this assumption is not provided in the problem, then we cannot use MIPS as the performance metric. Okay. So this is important. CPU varies between program on a given CPU. Okay. Okay. So the performance part is over, and then now we will learn about power consumption of the computer system. So this is also important part because, as I mentioned, the power is the important research topic in the computer architecture field. So we need to reduce the power consumption of the computer system. Okay, so let's think about the power trend of the computer processor. So in this graph, this y-axis just mentioned shows the clock rate. That means the clock frequency of a computer processor. And then this black line represents the power consumption by the CPU processor. So you know the 8286 is a very old processor. So what is the clock frequency? The clock frequency is the 12.5 megahertz. Oh, it's very slow. So usually we are using even the mobile processor, so works with the over 2 gigahertz or over 1 gigahertz clock frequency. But this is the desktop CPU, is 8286, but the clock frequency of this old CPU is just 12 megahertz, not gigahertz. So, but clock rate increases continuously, and then it reaches 2 gigahertz with the Pentium 4 CPU. And then recently we are using core CPU, the core architecture. So the clock frequency of this core architecture is usually over 3 gigahertz, right? So but Intel also adjusts the clock frequency by some workload. That means the amount of some instructions executed during the unit time. So the clock frequency vary by environment. Well, let's see the power. The very old CPU just consumed 3.3 watts. So what is the unit of power consumption? It's 3.3 watts. very, very, very low. Even the mobile processor, the recent mobile processor consume about 5 watts. But just remember that this is a desktop CPU. But as you can see, the power consumption by desktop CPU increases dramatically, have increased dramatically. So recently, the TDP is a TDP of a desktop CPU is usually 65 watt, and recently the Intel Alder Lake reaches 90 watt. So it's very high compared to the very old CPU. And why power is it's critical for the computer system? The power consumption of a processor is directly related to the running cost of a computer system. Okay, because if we just consume electric power, then we need to pay for the consumed electric power, right? So it's related to the running cost. Also, the power consumption by CPUs, by a processor, is directly related to the manufacturing cost. Manufacturing cost is also critical because if the manufacturing cost is high, then we need to pay more money for the same CPU, right? So power consumption is the cost. It's very critical. Then, how can you calculate the power consumption of a processor? So usually in the CMOS technology, the power is calculated so actually we need to add the activity factor alpha, and then so actually this is the proportional. So power is the activity factor alpha multiplied by capacitive load. It's the C, so it's a capacitive load, and then multiplied by square of voltage, it's a supply voltage, and frequency. Okay, so we can easily write a power consumption equation such as the alpha, it's an activity factor, C V square F. Okay, and then actually this equation represents the dynamic power. So dynamic power means that the CPU is running, then power is consumed. The amount of consumed power while the CPU is working is the dynamic power. So that means even though CPU is not working, the power is consumed. So that is called the static power. But in this course, we just focus on the dynamic power, okay? So this is the equation of the dynamic power. Then if this value is high, then cost is high. That means it's not good, it's bad actually. It's the power number is high or it's so bad. So we need to reduce the cost of the computer system. Then how can you reduce the cost? So this is the activity factor. So that means that how frequently the component of a CPU is executed. That means it's touched. So that is the activity factor. Actually, the activity factor is influenced by software, but usually the activity factor is the usually constant. Okay, so we cannot reduce this part. How about the C? C is the capacitance of the circuit. So that means in this equation, the C is the summation of overall capacitance in the digital circuits. So I believe the most of students are computer science or computer science students. But if you took some electrical engineering course, then the capacitance is proportional to the area. So you may actually this is the I believe this is some common sense of the physics, right? I don't maybe. So the capacitance of a processor is actually proportional to the area of a chip, because the capacitance is proportional to the area of a circuit. Okay, and then voltage. So this is the supply voltage. So this supply voltage is determined by semiconductor technology node. How about the frequency? The frequency is also determined by circuit designs or the technology node. So in order to reduce the power, we need to reduce the area of a chip. Also, we need to reduce the supply voltage. Also, we need to reduce the clock frequency. Okay, but execution time is instruction count multiplied by CPI multiplied by T. That means instruction count multiply CPI divided by clock frequency. What's the problem? This part. So in order to increase the performance, we need to increase the clock frequency, right? Understand? But how about the power? The power is proportional to clock frequency. That's the problem. So in order to increase the performance of a CPU, then we need to increase the clock frequency. But problem is that if a CPU is running with higher clock frequency, this CPU will consume higher power. That's the problem. And then actually the supply voltage is also proportional to clock frequency. Actually. So if you are interested in overclocking the desktop CPU, then in order to increase the clock frequency, then we need to also increase the supply voltage to CPU, right? So actually the voltage is proportional to clock frequency. So that means the power is proportional to cube of clock frequency. So that's the problem. Actually, not easiest, but it's a direct way to increase the performance of computer system is to increase the clock frequency. But if the CPU is running with the higher clock frequency, then it will consume much power. That's the problem. So because of power, the performance of CPU is constrained. Do you understand? That's why the title of this chapter, this section, is called power wall. What is the wall? So this is the wall, and then if the wall is in the middle of the load, then we cannot propagate. That is the wall. So what does power wall means? Power wall means that because of power consumption, because of a power consumption issue, we cannot increase the performance of a processor. That is the meaning of power wall. Okay, this is another issue of the process of design. Okay, so actually based on this simple equation, we can easily compare the power consumption of the different CPUs. So that is the example. So this is the new CPU, and the new CPU has the 85% of capacitive load of on old CPU, and then 15% voltage and drop, and then 15% frequency drop. So what is the power consumption of this new CPU? So we can also easily use these numbers for this equation, and then we can compare the performance of two CPUs like this. Okay. So actually the power, I think the power, this equation is, if you just remember this equation, then I believe you can easily calculate the power consumption of compare the power consumption of two processors. Okay. And then I will explain about the scaling by technology, semiconductor technology node. Actually, this scaling dynamic power is called Dennard scaling. Dennard is the name of a person, it's a researcher, and then he just calculate the power consumption. I think it's the trend of power consumption by semiconductor technology node. Okay, so that's why this is called the Dennard scaling. So I will explain about the Dennard scaling because this is it's an important issue of current CPU design. So this is the equation of the dynamic power consumption, as I explained. So P is the alpha, is activity factor, and then C, capacitive load, and then V square is a V square supply voltage, and then frequency. So this is the power consumption equation. So we cannot change this alpha. The alpha is actually the activity factor is usually 1/2. Okay? We cannot change it because this is usually determined by application, but application usually touch every part of the CPU. So activity factor is actually very similar. Okay. And so in the previous classes, I explained that when the semiconductor technology is advanced, then we can shrink the width of a CMOS transistor channel. Okay. So it's not easy to explain, but this is the shape of the MOS transistor, and then this is called gate. So channel width means the width of this gate. And then usually, if the CMOS transistor technology is advanced, this channel width is reduced, which means actually the electrons are moved to the other part of this MOS transistor, and then this time for moving these electrons determines the speed of a digital circuit. Okay, so if this channel width is short, then the speed is increased. So that means if we use the more advanced semiconductor technology, that means that the node number is reduced, then we can make the faster chip, the faster processor. Also, this channel width determines the size of a transistor. Okay. If we reduce the channel width as 1 over S, so 1 over S, this S is the scaling factor. So for example, if the technology node is reduced from 20 nanometer to 10 nanometer, then scaling factor is 2. So which means the channel width of a transistor is shrink to half of a old technology. Okay. So in this case, the scaling factor S becomes 2. So width is 1 dimension. And then if we just consider the area of digital circuits, then area is 2 dimension. So if we reduce the channel width as 1 over S, then the area will be shrinked by 1 over S square. Okay. Oh. So this one. Oh, so sorry. So actually, so in the circuit, it's a MOS transistor. The C. So I said that the C is proportional to the area of the circuit, but in this case, the C is reduced to 1 over S. So it is because we just reduced just this width, not this part. So if this width is reduced by 1 over S, the C, the capacitance of a single transistor is reduced to 1 over S. Okay. And then also we can reduce the supply voltage to 1 over S. Okay. And then as the width of this CMOS transistor channel is reduced by S, then we can also increase the frequency as S, because the width of this transistor is reduced, the speed, we can increase the speed. Okay, so this becomes the S. Then what happened? The P is the alpha, the C becomes the 1 over S, and then VDD is becomes the S square, 1 over S square, and then multiply by S. So what happened? Alpha S 1 over S square. So what does that mean? As the scaling factor is with this scaling factor, that means that the channel width is reduced by S, then we can reduce the dynamic power of a single transistor by 1 over S square. And then, the size of a transistor is reduced by 1 over S square. So that means in the unit area, we can include the S square times of transistors. Right. Because the transistor size is reduced, then we can include more transistors in the same area. So the number of transistors becomes S square. So the dynamic power of a single transistor is reduced by 1 over S squared, and then number of transistors in a unit area becomes the S squared. So which means 1. So actually, the Dennard scaling means that if the semiconductor technology is advanced, then we can make smaller transistor. But with this smaller transistor, we can also reduce the dynamic power. But with this smaller transistor, we can include more transistors in the same area. And then actually, the power consumption of a unit area becomes constant because this is 1. That is the Dennard scaling. So what is a good thing of this Dennard scaling? If we include more transistors, then the number of transistors is the resource of CPU. And if we just invest more resources on a single CPU, then we can manufacture better CPU. So CPU that will have higher performance. But the power consumption is constant. So good thing of this semiconductor scaling is that with the same power consumption, we can build better CPU. So which means if we can use more advanced technology node with the same cost, we can build better CPU. That is the good thing of Dennard scaling. Okay. So this graph shows the trend of the technology node. So recently the Intel is using 10 nanometer technology. So this graph shows the width of the channel width of the most transistor. But how about the power per square nanometer? So that is actually power density. What is observed? So I explained that with the Dennard scaling, the power consumption in the same area is constant if we use the more advanced technology node. So the technology node has been advanced. So we can use the smaller transistor. So what is the expected power density? Actually, expected power density by Dennard scaling is this constant. Okay. This is the expected power density. But as you can see, the power density has been increased more and more. So what is happening? What is happening? What's the matter? End of Dennard scaling. The problem is that actually in the Dennard scaling, we just focus on the dynamic power consumption. So what is the dynamic power? So dynamic power means that when a CPU is working, the power is consumed. So amount of consumed power is called the dynamic power consumption. But So if we just consider the dynamic power, then the dynamic power consumption is constant. That means the power density of the dynamic power consumption. But as the technology node is advanced, that means that the channel width is shrinked, the power is consumed even if the CPU is not working. Then this power consumption is called static power. So I mentioned that even though a CPU is not working, the application is not running on this CPU, the power is consumed if the CPU is turned on. This power consumption is called the static power. So what's the problem? Because of this static power, the power density is not maintained. That means in the same area, much more power is consumed by a CPU. I said power consumption is very critical because this is cost of a computer system. So power density is increasing, which means our computer system will consume more power. Even the power semiconductor technology is advanced. So that's the problem. Okay. So when the Dennard scaling is maintained, then we can use better CPU freely. But recently, we can use better CPU while investing more money for power consumption. Okay, that's the problem. Okay, so I explained about the power issues of the computer processor, and then switch to multiprocessor. So this graph shows the performance of uniprocessor. Uni. So uni means single. So we just focus on the performance of a single core CPU. Okay. So what does that mean? So application is compiled to generate the machine code, and then this machine code is becomes the one thread. It's a single thread. It's a single thread is run on a CPU. It's a single core CPU, and then this graph shows the performance of a single core CPU. So let's see the performance trend, and then we just compare the performance of different processors over this reference machine, reference CPU. It's a very old CPU. So as you can see, the performance is increased continuously. But as you know, this y-axis is the log scale axis, right? And then this is nearly linear, which means the performance of a single processor is increased exponentially. Okay, so in the real life, the performance of a CPU is increased exponentially until early 2000. And then, you know, this slope of the graph is decreased. So recently, the performance of a single processor is nearly constant. What's the matter? What happened? Why? What's the reason? It's power. Yeah, it reaches the limit. Why is it saturated? It's because of power consumption. Yeah, so the performance of a unit processor is also increased by some development of the architectural techniques, or also the development of software, but mainly, I said mainly, the performance of CPU is influenced by advances in semiconductor technology. And then if we reduce the channel width of the MOS transistor, then we can increase the frequency. But because of end of Dennard scaling, like that is dynamic power alpha C3 square F, we can, in order to increase the performance of a CPU, then we need to increase the frequency. But as I explained, in order to increase the frequency, if we increase the frequency, then the CPU will consume more power. Okay, and then if the Dennard scaling is maintained, then the power density is nearly constant. So, but which means even though we increase the frequency of a CPU, then also we can also use the better semiconductor technology, then the power density is nearly the same. However, the power density is increased. So, which means even though we use the more advanced technology node, we cannot increase the clock frequency of a CPU. Understand? So I said, even though we use more advanced technology, so which means even though the technology node is changed to the 20 nanometer to 10 nanometer, we cannot increase the clock frequency. Why? Because of power. So this slight development, the performance improvement is actually benefit from architectural techniques. So usually from this point, this year, the clock frequency of a CPU is nearly the same. Okay, let's see this graph. In 2004, the clock frequency of Pentium 4 Prescott was 3.6 gigahertz. And then this clock frequency number is nearly same to the core CPUs, right? Intel Core architecture, right? The problem is that even though better technology node is applied, we cannot increase the clock frequency because of power consumption. Then, how can we use better CPUs? That's the problem. If we cannot develop better single core CPUs, then how can we use better CPUs or high performance CPUs? It's the multiprocessor. So recently, the most of the processor is multi-core processors. So for example, Intel i7, I think the Intel i7 includes the 6 cores recently, or 8 cores, maybe. So which means that in a single chip, multiple cores. So what is the core? multi-core means independent CPU. So which means a single thread, so single application can run on this single core. So what then if the multiple cores are fabricated in a single CPU, which means we can run multiple threads, like 8 threads concurrently in this CPU. And what's the benefit? So with this multi-core CPU, first we can increase the latency, we can increase the throughput. Which one is true? With the multi-core CPU, can you increase the latency of a thread? No. We cannot increase the, so we cannot, that means we cannot increase the performance of a single processor. That means the latency is not reduced. But with the multi-core CPU, we can increase throughput of a computer system. Do you understand? What is the throughput? Throughput means the amount of work done in unit time. So why do we use multi-core CPU? Actually, we cannot develop better single-core CPU because of power. But we want to use better CPUs. So instead of increasing the performance of a single-core CPU, we decide to increase throughput of a computer system with the multi-core processor. Okay, so with the multi-core processor, we cannot increase the performance of the single thread, but we can increase the throughput of a computer system. So we can increase the throughput. Okay, so that's why recently we are using multi-core CPUs, not single-core CPU. Okay. Okay. I will briefly explain about the benchmark applications. Then, so in the previous class, we learned how to compare the performance of two computer systems. Then, in order to compare the two computer systems, then we need to provide the same application. So what does that mean? If the application is different, like A and B, this different application will have different execution time, even though the computer system is the same. So in order to compare the two different computer systems, then we need to provide the same applications. So these applications are called benchmark. So we use benchmark applications to compare the two different computer system performance of two different computer systems. And then the most popular benchmark application in the CPU area is SPEC. So SPEC means the abbreviation of Standard Performance Evaluation Corporation. So actually, many companies attend this SPEC group, and then they also provide some applications, the SPEC benchmark applications. And then this benchmark is used for comparing the performance of CPUs. So in this course, I just take the SPEC 2006, but recently we are using SPEC 2017. So actually this 2006 represents the year, okay? So we are recently, the most recent version of the SPEC benchmark is 2017. So actually, this spec benchmark is the collection of applications. And then these applications are used for measuring performance of CPU. What does that mean? So in order to compare the performance of a computer system, we need to measure on execution time, right? So, and then it's very simple. It's the same applications like application A, B, C, D. And then these applications are run on the CPU. And then just measure the execution time. And then this execution time is compared with the execution time by reference CPU. So we can calculate the performance value by this spec benchmark. So this is an example. This is so actually the second edition of this textbook is published. So I just copied the table, this table from the second edition of the textbook. So this is the result of the spec speed 2017. So this is the integer benchmark. So that means that the integer instructions are frequently tested. And then this is the execution time on Intel Xeon processor. And then as you can see, every row represents the application. So like this is the application name, like a Perl bench. So and then you can find the description, this description of this benchmark name, then GCC, MCF, blah blah blah. Then you can find the number of instruction counts and then CPI for each benchmark. Then in order to measure the performance, we need to measure the execution time. Actually, clock cycle time is the same because it's the frequency. And then you can just measure the execution time on this CPU. And then what is this color? This is the reference time. So which means the execution time of this application on reference CPU. And we can calculate this ratio. How can you calculate this ratio? Like this is the execution time of B, and this is the execution time of A, which means it's a reference. So what is this spec ratio value? This is the performance. So this is the execution time of A divided by execution time of B. Right. So actually, this is the spec ratio. So as you can see, for the different application, the spec ratio value is different. So which means for a specific benchmark, the performance of this Intel Xeon is much higher compared to the reference machine or reference CPU. Okay. So for example, for the GCC, the performance of the Intel Xeon CPU is about 4.6 times faster than the reference CPU. About the data compression is lower than the reference CPU. And then we can generate the average value based on this spec ratio numbers. So this is the geometric mean of the spec ratio values. So which means usually, so we can say that Intel Xeon CPU is about 2.6 times higher performance compared to the reference CPU. So do you understand how the performance is compared and calculated by spec benchmark? And also we can also measure the power consumption of a system. It's a system, not CPU. Now, So we can use the different type of benchmark. This benchmark is called spec power benchmark. So with this spec power benchmark, we can just compare the power consumption, that is the watt, by workload levels. And then we just reduce some performance values with the consumed power. So spec power just measure the performance of a system by consumed power. Okay, so that spec power just measure the performance per consumed power. Okay, then how can you calculate this power consumption of a server CPU? The interesting thing is that, so this low represent the workload level, so which means it's a workload load. So 100% means that the CPU, the 100% of CPU resources are used for running this workload. Okay, so which means 100% of CPU resources are used. Then 10% means that only 10% of CPU resources are used for running this workload. And then for every 10% workload level, the performance is measured. Also, the consumed power is measured. The interesting thing is that no application is running on this CPU, this server system, but the power is also consumed. And then we can average this performance value divided by this power value. That is the score by spec power. So we can see some interesting fact here, which means the power consumption. The power consumption is not proportional to the workload level. So which means even though the workload level is 0%, that means that any program is not running on the CPU, but the CPU or the system is consuming power. So that is the problem. And then if we just consider the running cost of a system, then if the power consumption is proportional to the performance, this is the good system. But in reality, the performance of a system is not proportional to the power. So this is another research topic of the modern server system. Okay, so I briefly explain about some benchmark applications that can measure the performance of CPU and power consumption. Okay. Then in the next class, so we will learn about the Moore's law. So and then in the next class we will conclude the chapter 1 of this course. Okay. So I will stop here. So do you have any questions?
Class on Wednesday is going to be in person?
Yeah, it will be in-person lecture. The in-person lecture will be provided. Okay. Okay. Thank you for your attention, and then see you in the next class.